2022 AB, number 2, calculator active, fun problem. Let f and g be the functions defined here and here. The graphs of f and g, shown in the figure above, intersect at -2 and x equals b, b is greater than 0. So I don't know this x value. Clearly it's a little less than 1 if this is scaled correctly. So find the area of the region enclosed by the graphs of f and g. Don't make it harder than it is. Top minus bottom. Here's the problem. We don't know where they meet. Good thing it's calculator active. All right, I've already typed them in. I'm going to go to a standard window, zoom 6, and you'll see here what you see on paper, and we're going to find that point of intersection. We already know the other one is at 2. So let's find that point right there, second in calc. Second in calc, there it goes, point of intersection, and first curve enter, second curve enter, guess, just be close to it, and we are. And that's it. This is the x value where they intersect. Currently, my calculator thinks that is x, so let's quit and take x and store it as b, and b, because, well, they said so. So that's it. They do need to know that you know this, so we're going to write that down. So here goes, number 2, part A. We know that capital B equals this thing that the calculator just said, which was 0.781975144. Round that off on paper if you like, but the calculator needs to keep that level of accuracy. And we are going to find the area. The area enclosed between two curves, again, is top minus bottom, and this is f, and that one's g, so it's going to truly be f minus g. The integral from -2 to b, no need to write all the decimals, we have already defined what b is, and they will be looking for that, is f of x minus g of x. There we go, and we're just going to type that in the calculator, see what we get. By the way, we've already earned 2 points on this one. Math 9, -2 to b of alpha trace y1 minus y2. Make sure you put those in the correct order. Your sign will be off if it's not. And it can just kind of screw you up a little bit if you're not careful. So 3.604. That's it. Let's go ahead and score this thing. We just earned 3 points. And here it is. We got a point for this. We got a point for, whoops. I said we got a point for this. It's actually the limits of integration. Let's extend this a little bit. It's all this right here, defining what b is and just putting it from -2 to b. Then we got a point for this, and we got a point for this. 3 points so far. This one looks like it's eating the other two. All right, all that was part A. Let's do part B. For the interval from -2 to b, let h of x be the vertical distance between the graphs of f and g. We kind of already used that idea, the distance here, right? So what we did in part A, just to conceptualize this for you, was to accumulate an infinite number of distances, an infinite number of lengths, and that became area. So this was the accumulation of a lot of area from this distance, this distance, this distance, this distance, doing all that. You've seen that before. Just wanted to reiterate that. Find the vertical distance between the vertical distance between the graphs. Yeah, I'm just stuttering. How about that? Is h increasing or decreasing? Well, here's h, and it is the vertical distance from f to g. Again, you've seen that. Is h increasing or decreasing? That sounds like a derivative issue to me, so let's take the derivative. The derivative of f minus g, that's not product, it's not quotient, it's not chain, it's just subtract them. So that's it. There it is. I want to know if this is increasing or decreasing at a specific value, -0.5. That 0 in the front, of course, is optional. I like it for aesthetic reasons. Otherwise, it just looks empty to me. There's that. And we're going to figure out what this is and then give a reason for your answer. I need to know if it's increasing or decreasing, so I really just need to know if this is positive or negative. So here goes. Math 8 in deriv. The derivative with respect to x of y1 at a specific value minus the derivative with respect to x y2 at a specific value. And I got -0.6. That is good to know. All right, that -0.6, clearly we can round that, is indeed negative, right? Because it's -0.6. And for that reason, we know that this is decreasing. So here goes. Because h prime of negative 0.5 is negative h of x is decreasing at x equals negative 0.5. Okay, let's make some sense of this, by the way. At negative 1/2, as we proceed and as we move forward, the gap here is getting just a little bit narrower, just a little bit. So negative 1/2 is about right here. So we have a gap that's this wide. And then as we move forward, the gap gets just a wee bit narrower. So yeah, that is decreasing. Okay, hard to tell from the picture, but that's the visual for it. All right, let's go ahead and grade this thing. We got a point for basically taking the derivative of this and just considering that, and then we got a point for our answer with our reason, and our reason does need to say this in some way or other. All right, there we go. Let's tackle part C. The region enclosed by the graphs of f and g is the base of a solid. Anytime you read that, start thinking, okay, I need to remember some area formulas. Cross sections of the solid taken perpendicular to the x-axis are squares. Stop and think about it. This distance from here to here is the edge of a square, and that square comes up off the page. So this distance, it comes up, comes over, and then this distance right here, from here to here, comes up and over. That's what it's doing. So we want to find the volume of that solid. You do not have to write what I'm about to write in green over on the side of the page, but the area of a square is the length of the side squared. When I taught this and when I had filmed a video on this, I used that to guide what's about to happen, because an integral is the accumulation of something. Generally, it's the accumulation of lengths to create area. Now we're accumulating areas to create volume in this case. So we're accumulating areas of an infinite number of squares. So it's square here, square here, square here, an infinite number of them from -2 to positive 0.78, blah, blah, blah. And that will accumulate to give us the volume. So from -2 to b of the length of the side. The length of the side is f minus g. F of x minus g of x, you could just put f minus g, and that whole thing is squared because of this, and we'll type that in carefully because we can get a little bit off with our parentheses if we're not careful. So math 9 from -2 to b, which of course is stored in our calculator. I'm not going to be able to put a square outside the automatic parentheses, so let's start new parentheses. So y1 minus y2, close those, square that, dx, final answer, 5.340. Don't leave that 0 off. But it's just a 0. I hear you. They want 3 decimal places, unless this truncated. If this was truly 5.34, nothing else, then you'd be fine. But it's 5.340, blah, 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 put the 0. All right, part D. The more you read part D, the more you'll realize the kind of problem it is. A vertical line in the XY plane, make sure you're visualizing it. There's a vertical line, and it is traveling from left to right along the base of the solid described in part C. Okay, we still have this 3-dimensional thing that has bases that are here, and the cross sections are squares. And we now know its volume, whether we need that or not. The vertical line is moving at a constant rate of 7 units per second. Why did they tell me that? Often when I see these things in this context and they say, this is happening and this is its rate, and then they ask for another rate, this is a related rates problem. And the best strategy I have for a related rates problem is to just start throwing everything I have at it by listing what I know. So let's start. The vertical line is moving at a constant rate of 7 units per second. What's changing? The vertical line. Well, when I first read this, I thought, well, what's the variable for that? Well, it's moving left to right. So I'm going to call it the rate at which x is changing. Call it dx dt if you like, which actually is going to be the correct thing to call it because it is moving, it's a vertical line, so it's perpendicular to the x-axis. And it is 7 units per second. There we go, we'll put that. And then find the rate of change of the area of the cross-section above. We'll talk about that in a minute. Almost said talk about and tackle at the same time. We'll tackle about that one. With respect to time, when the vertical line is at this position. Again, here's another indication that dx dt is the variable you would use. dx dt equals x is 0.5. Okay, so the area of what? The area of a cross-section, which in part C, they said were squares. So the area of a square is the length of the side squared, which is f minus g squared, okay? So we need to take the derivative of this, and we're going to. So let's do it. So here goes. Instead of writing f and g, I'm going to actually write the functions because I've worked this out and I tried it without it and it turned out to be a mess and I had to back up. So to save the time, I'm going to just go ahead and do that. So a equals natural log of x plus 3 minus x to the 4th plus 2x cubed. So I'm going to call it minus 2x cubed because we're just subtracting the whole thing, and we're going to square it. Now, if you're like, well, I'm going to FOIL this, but it's really 3 terms, so I'm not FOILing it. Don't. Okay, trust me. We're going to take the derivative with respect to time. This is where things can get tricky. Left side's pretty easy. Right side, chain rule. Don't make it harder than it is. Don't multiply all that out. Please don't. This is all squared, chain rule, so 2 times all this. If you want to call this f and g, you may, and I'm going to in the calculator in a minute, but I wanted this visual so we would know what we're doing. There we go, and that's to the first because we just chained it. And we're going to multiply by the derivative of all this, which is the derivative of the natural log of x plus 3 is 1 over x plus 3 times the derivative of x with respect to time. Okay, remember, if I'm going to take the derivative of something, here goes, we'll take the derivative of a with respect to time, then, oh no, that's t, that's an a, I need this. It's chain rule reasons. So d dt this side, and when I do, I'm taking the derivative with respect to time, and there's an x, so I need dx dt. Okay, minus the derivative of this, so 4x cubed dx dt, minus 6x squared dx dt. I'm running out of room, it looks terrible. No, now if you want to save yourself the trouble and the fact that that looks terrible over there on that side, it says dx dt at the end. The dx dt can factor out of all 3 of these terms. I'm not going to. But what's about to happen is we are going to evaluate dA dt at a specific time and place, and that is where x equals negative 0.5 and where dx dt equals 7. So let's go. 2 times. Okay. I'm going to switch back to using f and g now. So f of negative 0.5 minus g of negative 0.5 times 1 over negative 0.5 plus 3 minus 4 times negative 0.5 cubed minus, by the way, I'm about to factor out this dx dt, minus 6 times negative 0.5 squared. All that times, this is tragic looking, 7. I just factored dx dt out of that, ran out of room, going to put it at the end there. Let's do it. Okay, it's a mess, but thank goodness for calculators. 2. F evaluated at negative 0.5, alpha, trace, boom, negative 0.5, you can do that. Minus G evaluated at negative 0.5 times. All right, now it's going to get fun. Feel free to type that, or the calculator will do it for you. It is calculator active. Math 8. The derivative evaluated at negative 0.5 minus the derivative of G evaluated at negative 0.5. Close those parentheses. I just closed all these parentheses here. Multiply it by 7. I hope I get negative, where have I done it before? Negative 9.27. Yay, it worked. I'm not surprised, but I did type it slightly differently this time. So negative 9.272 what units per second? All right, let's see what we got. Oh, I never scored part C. Let's do that. The integrand on part C is worth a point. That would be this guy right here. And then the final answer. And then part D, we're going to get some points for this. Only 2 points. How sad. All that work, only 2 points. We got... well, we get a point for the final answer. But I'm also looking at their scoring guidelines, and they did it differently than I did. Yeah, we're good. We're good. Now, it turned out to be a big, nasty mess. What they put in, you can see it in the scoring guidelines, was they took the derivative of a of x, which was dA dx times dx dt, and they represented it very differently. Yeah, okay. As I looked through the scoring guidelines, I realized that this is a valid answer, and it should be, because it's correct. There we go. We've earned our points.